Nay discovery. Water-rich interior of exoplanet K2-18b. Imagine discovering a planet beyond our solar system that might harbor liquid water, the key ingredient for life as we know it. That's precisely what scientists are investigating with K2-18b, a sub-Neptune exoplanet that's capturing the attention of astrobiologists worldwide. But here's the big question. Could this distant world actually host oceans beneath its atmosphere? Temperate sub-Neptunes, like K2-18b, are particularly exciting because they orbit their stars at a distance where temperatures could allow liquid water to exist. These planets are larger than Earth, but smaller than Neptune, and if they possess the right conditions, specifically a water-rich composition and not an overwhelmingly thick hydrogen-helium atmosphere, they could potentially sustain liquid water layers beneath their atmospheric veil. This makes them prime targets in the search for extraterrestrial life. Previous studies of K2-18b had already hinted at a potentially intriguing atmosphere. Scientists detected an atmosphere dominated by hydrogen, H2, with significant amounts of methane, CH4, moderate evidence for carbon dioxide, CO2, and even tentative signs of dimethyl sulfide, DMS. DMS is particularly interesting because on Earth, it's primarily produced by marine organisms. Its presence on K2-18b, if confirmed, could be a tantalizing hint of biological activity. But here's where it gets controversial. The detection of DMS was only tentative, meaning more data was needed to be sure. Now, thanks to the powerful James Webb Space Telescope, JWST, we have a much clearer picture. A new study presents 4 new JWST observations of K2-18b as it passed in front of its star, a transit. These observations, using the near-infrared spectrograph, NIR-SPEC, allowed scientists to analyze the light that passed through the planet's atmosphere, revealing its composition with unprecedented precision. The results are compelling. The data robustly confirms the presence of both methane, CH4, and carbon dioxide, CO2, allowing scientists to precisely measure their abundance. This firmly establishes that K2-18b is indeed a water-rich planet, suggesting either a thick atmosphere with more than 10% water or a thinner atmosphere above a liquid water ocean. And this is the part most people miss. The distinction between these two scenarios is crucial for understanding the planet's potential habitability. Interestingly, the JWST observations didn't detect water vapor, H2O, ammonia, NH3, or carbon monoxide, CO, in the atmosphere. The absence of water vapor could indicate an efficient cold trap, where water freezes out at higher altitudes, preventing it from reaching the upper atmosphere, where JWST can detect it. The non-detection of ammonia and carbon monoxide supports the idea of a small, hydrogen-rich atmosphere sitting atop a liquid reservoir. However, the researchers acknowledge that alternative atmospheric models that include these gases can also fit the data within the margin of error, emphasizing the need for even more detailed observations. What about DMS, the potential biosignature? The new data only shows marginal signals of DMS, as well as methyl mercaptan, CH3SH, and nitrous oxide, N2O. None of these exceeded a 3 sigma confidence level in the models, and all fell below 2 sigma, without assuming a strong haze in the atmosphere. This means their presence is still uncertain. Furthermore, the researchers' photochemical models suggest that DMS and CH3SH could potentially form abiotically, without life, in massive hydrogen-rich atmospheres with high metallicity, a measure of elements from more of a heavier than hydrogen and helium. This is a crucial point because it highlights the challenges of using single molecules like DMS as definitive biosignatures. We need to consider other indicators and the overall planetary context. In conclusion, K2-18b remains a fascinating and promising target in the search for habitable worlds. Its cool, water-rich nature makes it one of the most compelling sub-Neptunes for exploring the possibility of liquid water environments on planets unlike our own. This motivates further, in-depth characterization of its atmosphere and interior. But here's a thought. If K2-18b does have a liquid water ocean, what other conditions would need to be present for life to potentially emerge? Could the high metallicity of its atmosphere actually hinder the development of life, despite the presence of water? What other biosignatures should we be looking for beyond DMS? Share your thoughts and theories in the comments below. Unraveling K2-18b. Non-equilibrium chemistry insights from JWST and HST. Finding habitable Earth-like planets is astronomically challenging due to their faint signals and small size. But M-dwarf stars offer our best shot at discovering smaller worlds like sub-Neptunes, the most common exoplanets we've found. K2-18b stands out as a temperate sub-Neptune orbiting within its star's habitable zone, with Hubble and James Webb Space Telescope observations revealing a hydrogen-rich atmosphere containing methane and possibly carbon dioxide. But here's where it gets controversial. Conflicting interpretations of these observations underscore how non-equilibrium chemistry, dynamic atmospheric processes that defy simple equilibrium models, is absolutely critical for determining key parameters like atmospheric metallicity, the abundance of elements heavier than hydrogen helium, carbon to oxygen ratio, CO, and vertical mixing intensity, KZ. This study tackles that challenge head-on using the Freckle non-equilibrium chemistry model alongside JWST data, generating spectral models across a 3D grid of parameters to match observations. While we use a simplified temperature-pressure profile, acknowledging this as a limitation, our best fit model strongly favors high metallicity, around 266 times solar at 2 sigma confidence, and an unusually high CO ratio, above 2.1 at 2 sigma. Methane detection is rock solid, but carbon dioxide remains maddeningly uncertain due to spectral noise. Surprisingly, the vertical mixing strength KZ showed no clear influence and remained unconstrained. Crucially, our non-equilibrium models outperform flat, featureless spectra by over 4 sigma, definitive proof of real atmospheric complexity. Trace gases like water or ammonia might lurk beneath the dominant absorbers, but standard constant abundance models simply can't capture this reality. And this is the part most people miss. That sky-high CO ratio isn't just a number. It hints at possible aerosol hazy particle formation, dramatically altering how we view this world's potential habitability. Does this mean K2-18b is a hazy, lifeless realm, or could such chemistry unexpectedly support life? While higher precision data from JWST's NIR-SPEC G3958 instrument and future DLT and S observations are essential for resolving these questions, one thing is clear. Ignoring non-equilibrium processes gives us an incomplete, potentially misleading picture. What's your take? Could complex atmospheric dynamics like this actually enhance the prospects for life in unexpected ways? Or does high metallicity fundamentally limit habitability? Share your perspective below. Authored by A.Y. Jaziri, O. Sohir, Ovino, and Carrasco. Submitted to RIV 250714983. K2-18b, discovering Earth's distant twin, the ocean exoplanet that could harbor alien life. Ocean worlds beyond Earth. The stunning discovery that could change everything. In a groundbreaking revelation that challenges our understanding of the cosmos, scientists have identified what might be the most promising candidate yet for extraterrestrial life. Meet K2-18b, an enigmatic world that's rewriting our expectations about what's possible in the vast expanse of space. Located 120 light-years away in the constellation Leo, this remarkable planet was first spotted by NASA's Kepler Space Telescope in 2015. But here's where things get really interesting. Unlike countless other distant worlds we've discovered, K2-18b sits in the sweet spot known as the habitable zone, a region around its star where conditions could support liquid water. But don't picture another Earth just yet. K2-18b belongs to a fascinating category called super-Earths, tipping the cosmic scales at 8.6 times our planet's mass. While that might sound intimidating, it's still considerably smaller than ice giants like Uranus or Neptune. This unique size makes it an invaluable case study in our search for otherworldly life. Now, here's the revelation that sent shockwaves through the scientific community. In 2019, researchers detected something extraordinary: water vapor in K2-18b's atmosphere. This wasn't just any discovery. It marked the first time we'd found water in the atmosphere of a potentially habitable exoplanet. Using the legendary Hubble Space Telescope, scientists identified the unmistakable signature of water molecules dancing high above the planet's surface. But here's where it gets even more fascinating. Some scientists believe K2-18b might be an ocean world, completely enveloped by a global sea beneath its cloudy atmosphere. Imagine an entire planet wrapped in a vast, mysterious ocean. The possibilities are mind-boggling. The burning question, of course, is whether this distant world could harbor life. While its stronger gravity and intense conditions might rule out life as we know it, the possibility of microbial organisms surviving in its atmosphere or beneath its hypothetical ocean remains tantalizingly real. And in 2023, the James Webb Space Telescope added another piece to the puzzle by detecting molecules like methane and carbon dioxide, compounds that on Earth often signal biological activity. Studying a planet so far away presents incredible challenges. Scientists can't simply snap photos. Instead, they employ an ingenious technique called transit spectroscopy. When K2-18b passes in front of its star, telescopes analyze the starlight filtering through its atmosphere, revealing its chemical makeup one molecule at a time. It's like reading a cosmic fingerprint from trillions of miles away. K2-18b represents more than just another distant planet. It's a testament to human ingenuity and our relentless pursuit of knowledge. Each discovery about this mysterious world helps refine our understanding of the universe and pushes the boundaries of what's possible in space exploration. Perhaps most importantly, K2-18b challenges our perception of Earth's uniqueness. It suggests that ocean worlds might be more common than we thought, hiding beneath alien atmospheres throughout the cosmos. The implications are profound. If one such world exists relatively nearby, how many more might be out there? But here's a controversial thought to consider. Could our focus on finding Earth-like conditions be limiting our search for life? What if life exists in forms we can't even imagine, thriving in environments we consider impossible? What do you think? Could K2-18b be harboring life in its vast oceans? Or are we too eager to find similarities to Earth in our cosmic neighbors? Share your thoughts below. The universe is full of mysteries, and your perspective might help unlock the next great discovery.